Measurement and Evaluation by Andrew Fry, Ph.D. and CSCS.
Another kind of test that can be performed is the hexagon agility test. Now, if you remember our definition of agility, we said it's not only the ability to change directions, but also body positions. And this test is a little bit of each. Instead of sprinting between direction changes, we're using a very short distance hopping test. The test is performed on a six-sided figure, which is a hexagon that is put on the ground with 18-inch sides. And the individual starts in the middle of the hexagon and is always facing the same direction. They hop over one side to the outside of the hexagon and then back to the middle. Then they hop over the next side and then back to the middle and then over the next side in succession until they've done that for 3 complete trips around the hexagon. And the dependent variable is typically how long it takes them to do that. They are not allowed to land on the line, and they're not allowed to turn and face different directions as they go. Another variation is you can see how long it takes to, how many different sides they can jump over in a set period of time. Now this test has been found to be a fairly good indicator of tennis playing ability when they've looked at elite junior tennis players. But there is a huge familiarization curve, and it requires a considerable amount of practice. In the first few times, you'll probably see quite a bit of improvement simply because this is quite a different task and the people need to become familiar with it. But it is a fairly well validated test. Now, I said we would add a little twist to agility. In an actual competitive setting, if say we're talking about an athlete, but it doesn't have to be just an athlete, the ability to change directions is important, but also the ability to choose what direction is important. Because in the training scenario, you may know what direction you're going to change, but in a competitive setting, you might have to respond to how an opponent is moving. This is a Nelson Choice response test, and what we see is we see 3 cones set up, they're 5 yards apart. And the person is going to start in the middle. Now the person administering the test here has both hands up in this case, and the runner doesn't know which way they're going to have to turn and run. Upon the signal from the tester is going to show, okay, whether you're running to the right or to the left, and upon that signal, the runner is going to turn in either direction and run as fast as they can past the cone 5 yards away. Now this tests how quickly they can turn and move, but it also tells you how quickly they can process that information. They see the visual signal. It has to go through their visual sensors, their eyes. They have to process that signal in their brain, and they have to tell their body, okay, I need to move to the right or to the left, and then go. And that takes time. This gives people 2 choices. They can't lean one way or the other in anticipation because they don't know which way it will be. Typically, 3 trials are done in either direction. They're done in random order, and you take the best performance in either direction. You may see a preference for one direction or the other. This could also be changed where you give more direction choices. For example, the person could go forward or backward. And the more choices they have, the longer it takes them to process that signal. Now, this can be done in a testing situation, but this is also very similar to certain drills that a lot of coaches do. For example, football coaches may have their athletes move forward, move backward, move left, or move right, and they have to respond to a signal. So this is simply one way of testing the ability to integrate and process that signal. Let's talk about speed. The ability to move from point A to point B in as quick a time as possible, as short a time as possible. And this is typically a short distance test. Now, a mile run is also a measure of speed, but that we would put in the category of an endurance test. This is measures of maximum speed, which have to be short in nature due to their physiological characteristics. We're going to talk a little bit about starting positions and how they're timed. We'll talk about whether people start from a static position or a moving position, a flying start, and how do we actually give the commands for starting them on these tests. And some of these are very practical implications for administering the tests. Now, there are a lot of different ways a person can start a sprint test. Here we see a couple individuals, and they're at the starting line. They already have their lead leg set right up to the starting line, but not over it, and their arms are in opposition. because they're already getting ready for the very powerful arm action that has to accompany a maximal sprint effort. So having that opposing arm in a back position and really almost exaggerating that to help them out of the starting position. Now occasionally you get an individual who likes to move around a lot. Let's talk about different ways to time it. In both of these pictures here, you might be the timer at the far end of the sprint test. In one case, I have an assistant there with an arm up that's going to actually give the start signal, and I'll watch their hand go down, or I'll listen for their voice, and I'll start the watch whenever I see the signal from my assistant. That means that the person, this is very much like a race setting where the person, the runner, is responding to a signal. Many times you may be out there administering it yourself. And on the right side we see the sprinter, the person being tested, holding a steady position, and you start the watch on their first motion. Now, you're going to end up with much shorter times using this method because you're not timing their reaction. You're simply starting the clock after they've already started moving. So you'll see a difference in the times. But if you always test that way, at least it's consistent and reliable. Occasionally a person gets in that position, they don't hold still. They rock back and forth, and it makes it very hard for the timer. Occasionally we'll have that person put their lead hand down on the ground just to keep them from rocking quite so much. So that's just a little trick that sometimes we use that may be effective. Some individuals want to get down into a sprinter start like they're in sprinter's blocks. And unless you're a highly trained sprinter, you probably are not very effective at coming out of that position, even though it looks like everyone could do better. There is a considerable amount of technique. So this standing position is probably the easiest. When you use your stopwatch too, don't assume that all stopwatches are the same. Make sure you know which buttons to push. If I push the wrong button and one of my people takes off sprinting and I have to send them back and telling them that I don't have a time on them, I didn't know how to run the stopwatch, it's not going to make them very happy. So know ahead of time simple things like, how do you run the stopwatch? Is it a mechanical one that needs to be wound? Then wind it. Does it require a battery and have a fresh battery that's still working? Good. Or replace it. How hard do you have to push the buttons? Some of them are very easy to trigger, some are hard, and you might have a misfire because it's too easy or too hard to push. So these are simple things, but things that need to be considered. Also consider what finger you're using. And a lot of people have a tendency to use their thumb. Typically you use your index finger, and which has a little bit faster response time than on a thumb. So at least be consistent. Here's an example of a flying start. My assistant is down there, and as soon as the runner runs by that starting line, which we can't really see here, as soon as they run by it though, he's going to give me that visual signal and I'm going to start the clock. This removes much of the acceleration phase, and this allows me to look at top end speed. Once the person gets rolling, how fast can they go? And this might be important. If I'm a track coach, it might be important for telling me who runs which leg on a relay team, because a relay sprinter, 3 of those runners have a running start. They have a flying start. So if I have some runners that don't have particularly fast accelerations from a dead stop, I'll put them maybe later in the second, third, or fourth leg. But this is called a flying sprint. The surface that you use could be very important. On the right I see a nice AstroTurf surface. It's forgiving, it's got a little cushion, it's pretty fast. But a lot of places don't have access to that. In fact, on the left we see some, I don't really like to put individuals on a hard tile floor, but if I'm at a lot of high schools, that may be where I have to sprint, especially if the weather doesn't cooperate. Tile floors, some of them can be fast because they're hard, but some of them are slippery too, and so you get slow times because of the nature of how they're waxed. Likewise, if I'm running on grass, is it tall grass or short grass? Is it a rough field with holes and rocks, or is it a nice smooth surface? Am I on a wooden floor like in a gymnasium? Am I on a nice track? Well, is it a cinder track, or is it an all-weather track or an asphalt track? These can all affect the times that you'll get. And if you run and test your people on different surfaces, you may get different results that are a result of the surface and not a result of the training program. So try to be consistent. Even if you don't have an ideal surface, be consistent on the surface you test on. How do you measure speed? Well, the easiest way is a handheld stopwatch. And stopwatches can be measured down to 1/100th of a second, which is probably too much accuracy because how consistent is the human finger? Do you have enough precision to be consistently accurate down to 1/100th of a second? You can also use electronic timers where there's a little switch mat that measures when they leave their starting position, and then they break an electronic beam at the end of the race. This can be extremely accurate. The problem there is, for a lot of people, is you get slower times because you don't have a timer that is responding. In other words, if I'm starting the stopwatch after a person moves, well, they're already moving by the time I start the stopwatch. But the electronic timer starts exactly when they start. So the net result, for example, on a 40-yard sprint might be as much as 0.2 of a second different. However, it's extremely repeatable. And no one can say, well, you did a poor job of timing, coach, because you didn't run the stopwatch correctly. A method that's often overlooked is you can use videotaping of a person doing their sprinting. And if you set up cones at known distances, you can actually use the slow motion control on a typical VCR, and you can actually measure the stride length of an individual or the stride frequency over a period of time. And that's one way to measure performance, which is a little bit different. It's not typically done, but it can be an effective tool when you're trying to improve perhaps running efficiency. Let's talk now about another area, flexibility or measurements of range of motion. And we're going to talk about some common tests like the sit and reach test. We'll also talk about some devices that are trickier to use or not as commonly used like the goniometer, the latent flexometer. And we'll talk about what I would call some very functional tests that have some practical applications and some different ways to test the strength, such as assisted and unassisted flexibility. The sit and reach test is one that probably most people are most familiar with. And here we see an individual performing the test. They have their shoes off, so it's just stocking feet. Their knees are locked out. They're using a specialized sit and reach box that has a little gauge, or it's like a ruler across the top with a sliding marker, a sliding stop that goes up and down that ruler. And the person bends forward at the waist, keeping the legs locked out, keeping the feet flat, and putting the middle finger, or the third digit of each hand, right on top of each other, and slides forward and holds it for a couple seconds. Why do they hold it? Because there's a tendency to kind of bounce forward, and then the result you get is either because the person has kind of thrown the little marker forward, or they just are bouncing and using their momentum to get a good score, as opposed to being able to actually flex at the hips and move and hold that position. Some common errors: letting one hand reach more forward than further forward than the other. Real common is bending the legs, and the tester sometimes has to simply place their hand on the knees to keep the feet from bending. Allowing people to wear their shoes. That's going to change the results by maybe an inch, depends how thick the shoes are. A problem with this test is some people are very large and their feet don't fit inside that sit and reach box. So sometimes people have had to modify and let them kind of turn their toes out a little bit, but that does change the position and that can change the results. Does the person look forward or do they look down? And there's data out there to show that there's not a whole lot of a difference on that. Now this is a good measure for hamstring and low back and hip flexibility, but keep in mind this is not specific to other body parts. Doesn't tell me about shoulder flexibility or ankle flexibility or elbow or other areas. So there's a lot of normative data, may be an effective and valid measure for your purposes, but keep in mind it's only specific to certain body regions. Now I can use a goniometer, and a goniometer is a little bit like a protractor that you might have used in geometry class. And what it is, this is a device that measures the joint angle. And so I need to know a little bit of anatomy. So I need to know my anatomical landmarks. In this case, we're measuring knee flexion. In this case, we're measuring a very specific type of knee flexion. The person is in a sitting position, so they're flexed at the hip, and they're trying to see how much knee flexion there is. So the point of rotation of the goniometer is placed at the point of rotation of the knee. So it's typically the lateral condyle, the lateral aspect of the knee there. And the arms of each side of the goniometer need to go right up the midline of each limb. And if you are not accurate in positioning it, you can get some very erroneous results. Also, and this picture is a good example, some of these goniometers, you need a microscope to read the numbers. They're unbelievably small and they can be misread. So you may do everything else correctly, but you may be reading the numbers incorrectly. Now, this is a good example to talk about assisted or unassisted. In this case, this is an unassisted flexibility test. The person is just pulling that knee up into that position. And an assisted, though, would be where they or someone else, for example, grabs hold of their ankle and pulls that knee even to a more flexed position. So with some assistance or with some force application, that knee can go to an even smaller angle, but that would be an assisted range of motion, as opposed to can the person do it without external assistance? That would be unassisted range of motion. They both may be important measures, but they're different. Don't confuse the two, because if you measured it unassisted one time and you measured it assisted the other, you're going to get different results. So make sure that is not why you have a change in performance on this test. The latent flexometer is a little device, not commonly used, but can be very effective. And here we see we're measuring dorsiflexion of the foot. And basically, this device attaches to a body part. In this case, it's across the instep of the foot. And it needs to be running in the same plane as the movement. So we see that circular disc there. On that disc, it's hard to see here, but you have two rotating plates that rotate around, and they have a weight on them. And basically, you have the person move from one extreme of the range of motion. You set the latent flexometer to 0 degrees, and then you have them move to the other extreme of the range of motion, and you measure how many degrees of movement that is. It's a rotational degrees range of motion. You can measure a lot of different movements this way, but it takes a little bit of practice to use and to get it to cooperate with you. But it can be very helpful. It's not inexpensive, but it may be a tool that you like to use to measure certain ranges of motion, and the unit of measure is degrees of range of motion. Now, what I would call a functional test, a little bit more functional, and it's certainly a field test, very simple. I don't need a lot of fancy equipment. This one is for shoulder flexibility. And we see the individual laying on the ground, and they're keeping their nose in contact with the ground, and they're grabbing hold of a stick or dowel. You could go to the local hardware store and get a length of PVC pipe for about $1 or $2 and use it, or a piece of doweling. And you have, in this case, we have the person grab hold of that stick using a width that is equal to the biacromial width. And if you remember your anatomy, your acromion process is the bony process associated with your shoulder. Well, they need to be grabbing hold just outside that width, so that the width of the grip is specific to each individual. Someone with very wide shoulders grabs a little bit wider. And then they lay face down and they see how far off the ground they can lift that stick with their elbows straight. And the person either takes a meter stick, or in this case a measuring tape, and they measure the distance from the ground or the surface to the bottom of the stick, and sees how far that person can flex the shoulders. Now, in extreme cases, a person can go all the way around and lift that straight overhead, and I've seen that in some extreme cases, but it's not unusual. You get some people that can't even lift it off the ground. Now, I mentioned measuring to the bottom of the stick. If you need to make a decision where you're measuring to, and it's typically to the bottom or the underside surface of that stick, because if you measure to the middle or the top, that's going to add an inch or two, or possibly an inch to the measure, and change your results. There also are some adjustments to make for arm length. A taller person obviously has a longer arm, and they may move through the same range of motion as far as degrees of flexion at the shoulder, but the stick will be further off the ground because they have a longer arm. And there are adjustments that can be made to this. But this is a good measure of shoulder flexion flexibility. A functional test that I really like is the squat test. And this is a test where the person takes off their shoes so they're not affected, the results are not affected by the characteristics of the sole, whether there's a heel or not. They take about a hip-width stance and keep their feet flat on the ground, place their hands behind their head, and they squat as low as they possibly can, keeping their feet flat. Now there's two ways that you can assess performance. One shown here is measuring the internal angle of the knee using a goniometer. So the person has to hold that, and how far down can they go. Another way that I've seen used, but has some limitations to it, is measuring how upright the torso is. That's the segment between the hip point of rotation, or the greater trochanter, and the center of the shoulder rotation. And you can actually measure that. However, some people aren't even able to get down to a parallel. They're way above parallel on a squat, and they end up having a very upright torso, but it's not because they're able to squat well, it's because they can't squat well. So if you have a population that might fit that description, you wouldn't want to use that as your criteria measure. The further down you can get, the more effective you can squat into what's considered a functional position. Why is this functional? There's an awful lot of, for example, sport activities that require to keep your center of mass low. Maybe you're a lineman and you have to keep your hips down. Maybe you're a wrestler and you keep your body center of mass low. But let's say you're not an athlete. Maybe you're just an average person that has to get down in a chair and stand up out of a chair every day, or to get up and down out of a low stool, off a low stool. You have to be able to function from a position like this on a regular basis. So this has some real functional implications here and is easy to administer. Let's talk now about assessing body composition, determining what is the body made of. And typically you've got methods of assessment that will separate out lean tissue from fat tissue. Now, lean tissue is going to include an awful lot of material. It's bones, it's skin, it's hair, it's anything that's not adipose, that's not fats or lipids. But there are some methods that can separate out into additional compartments. We're not going to talk a whole lot about ultrasound. That is, people have been experimenting with ultrasound as a measure of the thickness of the fat pad for a long time. And I've heard some people kind of question of how valid an ultrasound method can be. But let me tell you this, anyone who has seen an ultrasound performed on a fetus knows what unbelievable precision there is there. So measuring the thickness of a fat pad is very simple for ultrasound technology. However, it is expensive and is not typically used in the field setting. You also have dual energy X-ray absorptiometry, which is where a very low X-ray exposure is made to the body, and it was actually developed to determine bone density. But an offshoot of that was that it also allows the body to be separated into three compartments. So now you have fat compartment, but you also have the lean compartment separated into bone and all non-bone. So now I get a little bit more precision in separating the body into different components. Some people have thought this is the new gold standard. It has a lot of promise. There are some limitations. One is that it is exposure to X-ray, and there are some considerations there. It is also very expensive, but it's becoming more and more popular. Today we're going to focus more on some methods that are more commonly found in the strength and conditioning profession. Specifically, we'll start with underwater weighing, which today we'll use as the gold standard. And then we'll also talk about using skin folds and bioelectrical impedance, as well as infrared interactants. Now, regardless of the method we use, we almost always have to convert the results from a measure of body density to a measure of percent fat. And in order to do that, we need to use some conversion equations, either the Brozek equation or the Siri equations, which for the most part, for most populations, will give very similar results. But it puts it in a unit of measurement that has meaning both for the administrator and the person being tested, percent fat. Body density is an important measure, but it's not as meaningful a unit measure for most people. We'll also talk a little bit about body mass index, which is a height and weight measure. It's the body weight divided by the square of the height. But it needs to be pointed out, this is not a measure of body composition. Body composition is actually assessing how much of your body is body fat. This is a related variable, but it is not a body composition measure. You might have a high body mass index because of a lot of musculature, or you might have a high body mass index because of a lot of adipose, a lot of fat. We'll talk about that in a moment. The same thing for the waist to hip ratio. This also is not a body composition measure, but is really an indicator of the distribution pattern, the pattern of distribution of fat on the body. So although these are not body composition measures, they are somewhat related. Now, underwater weighing or hydrostatic weighing has been the gold standard for body composition for a long time. It can be fairly expensive when done in its most precise manner, and it is very time consuming. The person is put on a scale and suspended in water. In this case, we see an underwater weighing tank. It could be performed with a specialized apparatus in a swimming pool, but the person is completely submerged, and they exhale completely until all that's left is a residual volume, and they hold very still down there, and a weight is being made. And this whole method is dependent on Archimedes' principle, which basically says that the difference in your weight on dry land and your weight in the water is the weight of the water which you displace. And to make a long story short, this equation allows you to go and calculate the density of the body. Now, if I know the density of the body, then I can use, as I mentioned a moment ago, the Brozick or the Seery equation, and we can determine percent fat. Now, as you can imagine, there's a number of possible errors. Does the person exhale as much as they can when they're under the water? That can affect the results. Do they hold still? Are they a swimmer or not? If they're a non-swimmer, they are not going to submerge their head. Are they an elderly person or in a disease state or a young child? You'll have problems getting them to submerge. Now, there are some modifications where adjustments are made if you do not put the head underneath the water and so forth, but again, this adds to some potential error. You also have a big assumption, and this assumption assumes that all lean tissue weighs 1.1 grams per milliliter and all fat tissue weighs 0.9 grams per milliliter. Now, this might be a good ballpark figure, but we know that there's some inherent error there. This system gives you a two-compartment model, fat versus lean. When done correctly, it is very valid. It's been compared with cadaver studies, and it can be very repeatable. But there's also room for making errors so that if you're not particularly trained and aware of some of the problem areas, you can get some very incorrect results. But this is the gold standard that most of the other methods are compared with. Probably the most commonly used in our profession, from a practical standpoint, are skin fold calipers. And here we actually see two types of calipers. On the left, we see a thigh skin fold being performed with a Skindex, which is a little computerized caliper. And what's nice about that is all the calculations are done right in it. You tell what equation you want to have used, it lets you take the measures, and boom, 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 up comes on the readout the percent fat. Next person. If you're doing large numbers, this is a very time-effective way of doing it. However, there are some limitations. It does not allow you to do repeated, take two samples, two measures at one site. It may not have built into it the proper equations, because it does have certain limitations on it. It gives you certain choices on equations. It may or may not be the equations you want. It's hard to calibrate. Each of these calipers have to have a certain amount of tension on it. The ones on the right are very common to a lot of places, Lang skin fold calipers. You also see Harpenden skin fold calipers, and there are several other models that are very good and effective ones, but they all should give about 10 grams per 10 square millimeters of caliper based on the caliper size, the head of the calipers. So can you calibrate these? Are these actually providing the proper tension? Quite often not. These can be returned to the manufacturers to have them calibrated, and they should be done periodically. Another issue is, are you actually taking skin folds at the proper sites? For example, we see on the right a tricep skin fold being performed. Quite often people tend to grab hold of that skin fold too high on the arm. It should be a midpoint between the acromion process and the olecranon process. And when correctly done, this is actually measured and marked so that you have the same site being performed if you have to do multiple measures, and it's being performed at the correct site. Sometimes the improper equation is being used. Believe it or not, I've heard of examples where people have used equations developed for females on a male population because the people being tested got results they liked a little better. Well, that's certainly an invalid use of it. Make sure you're using an equation that's for the gender that you're measuring and for the age group that you're measuring. Sometimes the site, the skin fold location may be a factor. Some people have certain considerations you cannot overlook, that being a certain level of modesty. And there are some sites that some people may be uncomfortable with, so take that into consideration. If performed correctly, there's about a 1 to 2% error when compared to underwater weighing. So it's not a perfect system, but when done correctly, can be a very valid and very time-efficient method. And again, this separates into fat and lean compartments from which percent body fat can be determined. If I know percent body fat and I know body weight, then I can calculate out how much of my body weight is fat. And if I know how much of my body weight is fat, I can also determine how much of my body weight is lean. So for some people, the lean weight may be more important than the percent fat or the amount of fat that the person has. Perhaps if they're trying to put on size and want to measure, well, how much of my body weight increase is actually lean tissue. Another method of determining body composition is using bioelectrical impedance. And in this method, a small current is sent through the body. And we see the person in the picture here lying down in the supine position. This is the position required for this assessment. And electrodes are placed on the back of the hand near the wrist as well as the top of the foot. And a small non-detectable current is sent through the body. Now, this current is dependent, how much current actually passes through the body is dependent on several things. One is how tall the person is. The taller the person, that means it has to travel up the arm, down through a longer body and a longer lower limb, and there's more resistance, there's less current. So one of the variables you enter into the equation is how tall the person is. You also must know that the current is dependent on how much adipose there is. Moist or water will conduct a current, and lean tissue is high in water content. Adipose tissue is low in water content, and it is a resistor to the current. So the less current I have going through that is usually indicative of more fat content. This measure, though, you need to know, is dependent on temperature, both the skin temperature as well as the surrounding ambient temperature. If you just came in from the sauna, that's going to affect the current, or if you just walked in from a snowstorm, it's 0 degrees outside or something, that's going to affect the results. This method is also dependent on hydration status. If you are very dehydrated, like right after a vigorous workout, and you are in a dehydrated state, you'll get a higher percent fat rating because you have less body fluids to conduct this current. Likewise, it's been shown that females at different times of the month in their menstrual cycle, if they have a predisposition to retaining water, that can affect the results. So you need to be aware of the hydration status. From this, though, sometimes some of the devices allow you to estimate water content, but they also give you an indication of the body composition, again, a two-compartment model. We also have infrared interactants, which is a method that uses infrared light that is sent down into the tissues of the body, and it is reflected back to a sensor as it reflects off different types of tissues. So it might reflect off the area where between skin and fat, between fat and muscle, between muscle and bone, and it uses this signal to give an indication of a measure from which body composition can be determined. Now, most of the devices use only one site, and it's shown in this picture here where it's measured over the biceps. So all these measures are based on a one-site assessment. And this device was actually originally used for determining the quality of grain, and a lot of the funding came from the U.S. Department of Agriculture. And it had some promise for the determining quality of grain. Essentially, it would determine the density of grain. Whether that transfers readily over to biological tissue like a human body is up for interpretation. As a result, there is some questionable validity on this. We also have height to weight ratios, which originally were developed by insurance companies. How tall are you, and what would be your ideal height? Now, this has run into some problems over the years because If someone is extremely muscular, they may weigh an awful lot for their height, and it's not because they're obese, it's because they might be extremely fit from a muscular standpoint. It does not account or measure for body composition, but it does give you an indication of, are you a typical weight for your height. And when you measure height here, we see the line going from the ear canal, or the auditory meatus, to the inferior border of the orbit, or the bony structure just below the eye. And when the head is in that position, that's the position you want to measure stature from. So you can measure your height, and you certainly have your body weight, and you can get a height to weight ratio. You can also use these to calculate body mass index, which is also another indication of your body weight as it relates to height. And the equation here, body weight divided by the square of height, gives you an idea of where you are from a normative perspective. Again, a person might have a high body mass index because they're very muscular, or they might have it because they're very obese. Finally, we can look at some important circumferences. For example, the waist to hip ratio. And here we see a measure of a hip circumference being made. A couple things to keep in mind when you take circumference measures. One is you can't use just any tape. You need a tape that is not going to stretch. That means it needs to be, for example, a metal tape or a fiberglass tape. If it is a paper or a cloth tape, those do stretch over time. Also, you need to make sure you're at the correct anatomical location. In this case, it's at the point of maximum protrusion of the buttocks posteriorly. We also need to have the tape perpendicular to the axis of either the body or the limb that we're measuring. And quite often that tape gets a little bit cockeyed, and that will introduce a large amount of error. The tape also sometimes twists, and people don't realize it, and that will add to the measure. Finally, another consideration is how much tension, or how hard you pull on that tape. You certainly need to pull it snugly around, but you can pull it very tightly, or you can pull it just a little tightly, and you can get quite a bit difference in the results. Now, a highly experienced person can consistently pull so that the tissue under the tape is just depressed slightly. But for people who are less experienced, there are devices that, like a Gulick handle, that is a spring-loaded handle that tells you that you are consistently applying the same tension to the tape. So those can help you increase the accuracy of getting circumference measures. If you look at the ratio between the waist and the hip, that gives you an indication of body fat distribution patterns. And be aware there's a huge difference in that ratio between the genders. So don't equate the values between genders for the waist to hip ratio. This briefly summarizes a number of examples of some tests that can be easily performed in a strength and conditioning setting. And it also has briefly provided an overview of how you treat and present some of this data so that it can be properly interpreted and used.
This concludes the measurement and evaluation presentation.